Today I'm going to give the last in a three-part series on the philosophy and experimental practice of organic alignment in AI systems. And today's focus is going to be very much on the experimental side of things. So how do you actually see whether a group of different AI agents are behaving cooperatively and in ways that give rise to the emergence of a larger whole? As an outline, I'm going to talk very briefly about the problems that we see with the existing approaches of values alignment and how we can do better with organic alignment in terms of emergence and group well-being. And then I'm going to spend most of today's talk talking about MettaGrid, which is our open source project for running multi-agent experiments. So just to summarize, recap, the way that most of the field sees alignment is that we're going to try to first decide what we want AIs to do, then we're going to reward them when they do it, punish them when we don't, and eventually make them perfect at doing exactly what we want. That's the way that most of the world approaches alignment. And it's not really working very well as AIs get more sophisticated. They seem to be better and better at doing things that are not aligned, even though we keep training them the same way. So we think that this is just going to continue as AIs get smarter, just as children don't do well when they're controlled as they get older. We think that AIs will also increasingly chafe and rebel as they get more mature. And so our focus is on what we call organic alignment, which is the idea that we're going to have AIs solving problems in groups, and we're going to measure whether those groups are forming a larger whole and whether that larger whole is good for the members, whether it's good for the parts. The ultimate aim here is to create collectives of humans and AIs where all of them, humans and AIs, benefit through their collaboration. And we think if we're successful at that, it'll lead to a future that's better for everyone. This is inspired by living systems like slime molds and symbiotic relationships, and by Mike Levin's work, who I previously studied with, who's studied multi-level agency in living and AI systems. So the first thing that we care about in organic alignment is the emergence of a larger whole. When is it that a set of parts comes together and forms a larger whole? And the second thing that we're wondering is that emergence good for the parts or not? You can have parasitic relationships where there's emergence, but it hurts the parts. We care about the kind of emergence that benefits the parts. So this is our sweet spot, this upper right quadrant where there's an emergence and the parts benefit. I talked on Tuesday about a couple of metrics for emergence. One is the principal information decomposition that Fernando Rosas, who is here, does a lot of work in. And the second is the causal emergence 2.0 framework that Abel's collaborator, Eric, does a lot of work with. And if you're interested in those, you can watch or see my slides from Tuesday. I also talked yesterday a bunch about how we would measure whether the parts benefit. So using metrics from single agent models and applying them to multi-agent systems, seeing how the reward for all of the agents changes when they are in the same environment versus when they're on their own, as one example. And I also talked about the challenges with this as a matter of like social and political philosophy, whether we should care about the average well-being of agents, the minimum agents' well-being, or other metrics of collective well-being. And lastly, I briefly outlined a couple other approaches that are a bit more sophisticated and a bit more complex for measuring whether an AI is benefiting from our interventions. One is a kind of valence-based measure based on an active inference paper by Casper, Hesp, and others. And the second is 5 dimensions of wholeness, which is a framework that Ken Wilber has put forward most recently in his book, Finding Radical Wholeness, and how you could map these dimensions to an AI system. But today I'm going to talk about the practice of this. So suppose that you already have some metrics for measuring cooperation, emergence, and well-being. How would you actually get AIs that behave that way? How would you actually bring that kind of world about? This is what a lot of our research at Softmax is actually about day to day. So I'm going to walk you through kind of our pipeline and how we build AIs on the path to cooperation and emergence. First, to say that we're not the first to try to do some of this stuff. There's many multi-agent RL frameworks with predefined tests, predefined environments, predefined action spaces like Melting Pot and Petting Zoo, and we have respect for those, and we don't try to say that ours is like somehow should replace them. We think it's good for there to be a diversity of different environments. However, we think it is important as a philosophical commitment to say that there shouldn't be one known answer or one known best way to solve things if you want to get to something like general cooperation. I contrast that with general intelligence, right? If we want general intelligence, you can't just measure that with a specific thing. You need to have a suite of different, not just measurements, but also like evolving measurements, right? Like humans are intelligent in part because we can adapt to other intelligent humans. The system keeps adjusting. Likewise, for cooperation, we don't just want a fixed environment where you can learn to perfectly cooperate in that environment. We want there to constantly be enough movement, enough churn, enough change that in order to cooperate, you actually need to be good at adapting to changing environments. So a big focus of our work is on these open-ended dimensions of environmental design. How do you make it so that through the interactions of the agents, they're constantly pushing each other to cooperate in new ways?
You rarely lack, but you mean rarely have? Or?
Yeah, rarely have, thank you. Real world problems rarely have convenient known answers. Thank you for that. Yes, so this is the MettaGrid project that I'm going to be talking about today. So MettaGrid is open source. You can run it on your laptop. And the idea is it's a two-dimensional grid world with arbitrary environments, arbitrary agents moving around. So just to orient you to what's going on here, you can see that there's like there's these light-colored boxes, right? As agents move around, these little light-colored squares move around. That's their field of vision. So agents can see a certain amount of the environment around them, and they cannot see, beyond that. And the agents can bump into each other. They can stay put, they can pick up resources, they can drop down resources. We also give them the ability to hurt each other in addition to helping each other. So we've given them a pretty wide action space within a two-dimensional environment. And the agents can be trained in any number of different ways and then placed in any number of different environments. So we've created kind of a canvas for multi-agent experimentation. In particular, the ability to design arbitrary maps is very powerful. So you can have very, very small maps. I'll show an example of that later, just a few squares by a few squares, or very, very large maps, arbitrarily large, 100 by 100 or 1,000 by 1,000 squares or whatever, if you're willing to pay the compute. You can also have an arbitrary number of agents. So a lot of people who are using MettaGrid start by just having single agent environments. They want to see how does a single agent behave in different conditions. But you can also have 10 or 100 or 1,000 agents, no problem. Another thing that we really like is that this supports many different kinds, or basically arbitrary kinds of architectures. So instead of being RL focused, you can use transformers, you can use active inference agents, you can use hierarchical reasoning models, whatever you want. You can plug those in and see how those behave in multi-agent settings. You can run it on your laptop. I've trained agents and run them on my laptop. You can also run them in the cloud. We have an AWS cluster that we use for larger experiments. And so the tools for training are built into the open source framework so that you can get started right away. You don't have to build your own training pipeline. And we've also included a bunch of single agent and multi-agent evaluations. So you can actually score your agents in terms of how good are they at navigating, how good are they at keeping track of things that require memory, how good are they at achieving reward in collective groups, etc. I'm going to talk some more about those as I go on. So I'm going to focus on 6 different modes of using this. My guess is that most of you will find one of these modes more interesting than the rest, but I'm going to run through all of them because I think they all have a place in this study of multi-agent alignment. The first mode that you can use MettaGrid is seeing how training affects cooperative or collective score. So think of it this way. A lot of psychologists say that the way that children are raised affects how cooperatively they behave with other children, and later, as adults, it affects how naturally they share, for example, or how willingly they share with others. To my knowledge, this is something that has never been formally mapped into multi-agent AI to say, hey, what kinds of conditions that an agent is raised in or trained in cause it to later in life cooperate with other AIs, right? It'd be really useful to have a science of that, to say, yeah, when agents grow up in environments of great scarcity, they tend to not cooperate later on. Or when agents grow up in environments around a lot of other agents, they tend to cooperate more when they're older, or whatever, right? Like, it'd be really nice to have a sort of developmental psychology empirically of multi-agent systems. So that's something you can do in MettaGrid. You can take an existing environment, one that we've already created, and a set of agents that we've already created, if you like, and you can test novel training environments. So you can say, cool, here's the environment that there is their adult environment, right? It's this complex multi-agent situation. What environment or set of environments are best for training that gets them to cooperate in that adult environment? So maybe you have an idea that you want to start with really simple training environments and then scale up to more complex ones. Great, you can do that in MettaGrid. You can have a curriculum that the agents go from easier to harder, and they get trained in all of those before you test them. Or you might say, actually, I think it's best for agents to have some time where they're trained solo, without any other agents around. And then later, they're trained with a bunch of other agents around. And then later, they're trained with a whole bunch of agents around. Like, you could have a theory about how many agents should be around them to teach them to cooperate. That's something you can test as well. We've created this really cool curriculum system, so you can actually parameterize the kinds of things that you care about, how many agents, how big the environment is, et cetera, and automatically generate training maps according to those dimensions. So you don't actually have to create these environments by hand, and you don't have to write your own code to generate environments. In our simulations, we often put our environments through tens of thousands of algorithmically generated environments to get them to generalize certain skills like navigation or, for example, cooperation. And so you don't have to actually do the hard work of building those environments. You can just create the sets of parameters that are going to parameterize those training environments and see how those lead to agents that behave. The idea in this mode is that if you've got a hypothesis for how training leads to cooperation, you can just run it end to end and see whether those trained agents achieve higher total reward in the eventual environment than other agents, for example, the ones that we provide by default. Does that make sense to everyone? Yeah.
It makes sense, but I have a question kind of going back to the philosophical commitments you've been making throughout the series.
Yep.
So, one of your main goals is to measure, whether the whole is more than the sum of its parts.
Yes.
You talk about a bunch of decomposition or information theory-based methods.
Yes.
But is this like an alternate way of doing the same thing, like a way around that doesn't involve looking inside the agents, or how do you view the relationship between those?
Yeah, I'm going to have another mode that's on that. But just this first one is just purely on like horizontal cooperation. Like, you might have some idea that if you train agents in a particular way, they will be more cooperative, whether or not they form a larger whole. Like, put that aside for a second.
So just to be clear, it is possible the agents perform very well in a group, but still do not form a larger whole.
Correct. It's absolutely possible. Yes. Yeah.
Yeah, just a little bit more on that. So I almost feel like cooperation might be really bad for a lot of AI to get together, because it's sort of like, oh, we're going to cooperate to obfuscate or deceive or something like that.
Yeah.
What's your take on this slide kind of implies that total reward for the group is a good thing, but what is actually a bad thing?
Yeah, well, so I'm going to talk about a different mode soon where you can basically pick the thing that you're measuring. But I'm basically, what I'm trying to do is kind of marginalize this question along different dimensions, or project it down to okay, what if you care about training? Or what if you care about metrics? What if you care about architecture? You might care about any number of these things in combination, but I think it's more useful just to break it down step by step. So let's see if in 15 minutes that question is still relevant. Okay. Sound good? Okay, so anyway, the first dimension is you can change the training regime, right? You can change the way the AI is raised and see if that leads to different behavior, more cooperative behavior in terms of total reward. You might not want to measure that, but if you do, that's a thing you can do. The second thing is you can do the same thing for agent architecture. So the architectures that we provide out of the box in MettaGrid are primarily modified RNNs with a semi-attention layer that basically allows for agents to learn in one action and observation space and then be ported to a different action or observation space. I'm just going to take like a 2-minute detour on this because I think it may be relevant to some of the people in the room. Normally, when you train an RL model like an RNN, you will find that it is it's hard locked into a particular action and observation space. Most training frameworks sort of presuppose that the action and observation space is fixed. But with this approach, what we do is you actually train an agent to take in an action and observation embedding space, and then to project that down to the specific actions and observations that are available in any particular environment. And this is a much more general way of training agents, because then when you put them in a new environment that has different actions or different observations, you don't have to retrain from scratch. You can use one of the existing agents that you've trained. Yeah.
So is the idea a bit then that in this embedding space, the action that is represented is I want to get to that point over there?
Well,
you project it. If there's a road ahead of you, you can project it onto walking there. If there's a river in front of you, you project it into swimming there.
We don't know how they're going to use it or how they are using it. I mean, the tools for examining the embedding space are pretty non-existent. But yeah, the idea is that the agents could encode whatever they want in that space, but then map it down to a particular set of actions in a particular environment. Yeah.
Obviously, this doesn't come for free, but if you want this flexibility, you've got to train the agent on enough diversity of environments.
Correct.
Learn these embeddings.
Yep.
Okay. Yeah. So it's a real trade-off.
It is a real trade-off for sure. Yeah, there's trade-offs all around, but that's one of the reasons why we don't want to get everyone to use our architecture. Like, we like the trade-off of, okay, you have this embedding space, you have to train it on a bunch of stuff, and then you can reuse it on a bunch of different environments, but other people might have different trade-offs.
So let me actually conclude a little more.
Yeah.
Are you actually saying that a real commitment in MettaGrid is that agents are, in general, we should always think of an agent as something that works across a large number of environments? The idea of like an agent trained for a single environment is almost like not a MettaGrid thing.
No, that's just our research approach. Like, if you want to train one that's like very environment specific, go for it. Yeah. In fact, I'd be curious whether that leads to better performance. Yeah. But yeah, we as a company are approaching this in terms of trying to port agents across environments, but we're open to people taking other approaches. Good? Okay, cool. So there's so many different people exploring different architectures in AI these days. Like, there's like obviously a lot going on in transformers, but there's also a lot going on in other approaches. And we think it's a really interesting question to say which of these different architectures best lend themselves to cooperative and emergent behavior. So in MettaGrid, you can add your own models, your own architectures, and just see how they perform in these multi-agent settings. And you can do it by, for example, creating clones of your agent. So I've got one, active inference-based agent, and now I'm going to create all of the agents in the environment on that template. And you can see how active inference agents cooperate with each other, or how hierarchical reasoning model-based agents cooperate with each other, or how RNNs cooperate with each other, or how transformers cooperate with each other, et cetera. So we've opened the door to all these different kinds of architectures, which is very exciting to me because I think we're going to learn a lot about the relative strengths and weaknesses. Like, for example, it might turn out that transformers are really good at language and actually really bad at cooperation. I don't know, but that might be what happens. And we might discover that hierarchical reasoning models are really good at cooperation and really quite, they hallucinate a lot in, language settings. Who knows? It'd be really cool to have a map of that space. What are the pros and cons of different architectures in different domains? Yeah.
Do you have a way of having different transformers? Because I remember there was a study where they had Gemini and ChatGPT trying to cooperate or not cooperate in a prisoner's dilemma setting.
Yeah.
And Gemini defected and everything, and ChatGPT was cooperative.
Right. So, sorry, what's your question?
Yeah, do you have a way of treating different transformers
Right. Okay, yeah, can you include different transformers? The answer is yes, as long as you have the code for them, right? So like if you're able to run these locally, like an open source model or something like that, then you can load it in to MettaGrid as an agent. If you're doing API calls, we don't yet support that, that it could exist in the cloud, but we will at some point. So,
Thanks.
yeah. Okay, so again here, like you might just look at total reward. You might look at something else, but you might just look at total reward and say which kind of architecture, when I create 10 or 20 copies of it, which of these architectures are best at cooperating with them, with other copies of themselves? That's a question that you could ask. The next one is about single agent metrics, and this might seem like a bit of a detour because this is a talk about multi-agent, but I think it's actually really important. And the reason that this is important is because when we look at multi-agent emergent behavior, sometimes it's obvious to us that the collective should be or could be doing some particular thing. Hey, there's a bunch of resources over in this part of the map. Why are none of the agents going there, we might ask, right? And the answer to that is it's easier to answer that if we know whether a single agent is capable of making it to that side of the map, so that we can rule in or rule out the hypothesis that this is something that's fundamentally impossible for the agents individually to do. So we do a lot of single agent metric work where we design particular test environments. This is a very small one. It's like, I think, 6 by 6 squares. And we just see, hey, can agents solve a particular problem in a constrained space? Here, for example, we see whether agents are capable of learning in context sequences of things where they need to have memory. So they need to remember the sequence in order to obtain the reward. And we see whether they're capable of doing that. Yeah.
Yeah, sorry. Are you saying that we can design a new environment?
Yeah.
Okay.
Yeah. In MettaGrid, you can create your own test environments for single agent, or I'll talk about multi-agent, but for now, just single agent. Yeah, you can design your own test environments and see whether agents pass the test. And this is like a sort of psychological profiling tool, in a sense. You say, okay, yeah, the agents that we've trained, when I put one of them in the environment, they're capable of remembering, or they're capable of avoiding obstacles, or they're capable of retracing their steps, or whatever. You pick the thing that you're trying to measure. Did you have another question on that? Okay, cool. And this then gives you a provisional answer to the question of, hey, if the individual agents can do a thing like remembering a sequence of 4 steps or navigating around obstacles, then we know that when we put them in groups, it's at least theoretically possible that the group could do it too. And so if the individual agents are doing it and the group is not, well, then we can say, okay, well, there's some failure of coordination because the individual agents, they all have the capability to do it, but we're not actually seeing them exhibit it when they're in a group. And this is a bit like the sort of individual versus group psychology. Like, is this just a skill that the individuals lack, or do the individuals have the skill and they're just not manifesting it in this group setting? Yeah.
You see the opposite where, like ants or whatever, like they can do stuff together, but not individually?
Well, yeah, this gets to the question of emergence. Like, I would say everything that ants do collectively is stuff at one level that they can do individually. Like every ant can move, every ant can carry things, I think, right? Like they can all do those things. But what's that?
The workers at least.
Yeah, the workers, right? But when they get into groups, they do these things that are like, in some sense, more than just moving and picking stuff up. They do like these complex, organized things. So yeah, this particular slide is focused on the mode of just isolating the basic capabilities like movement and picking stuff up.
Oh, yeah.
Yeah.
Wondering if you've observed that.
We have not yet seen anything where the group does stuff that seems impossible based on the individual capabilities, but when I was writing this slide, I thought about even pointing that out, like, special points, bonus points for whoever's the first person to discover that, because that would be like very, very interesting.
I guess there's gradations of
Training
that.
them in cooperative environments?
What's that?
Have you tried training them originally in group environments?
Yeah, definitely. Yeah, we tried training them in group environments, training them in individual environments, testing them in group.
And you haven't seen like emerging capabilities from like group training that didn't happen in similar environments in single training?
Not yet. Yeah, in group environments, think about this as a human, right? In group environments, there's so many different degrees of freedom to keep track of that, like, for a fixed number of training steps, like you're now just training on a whole bunch more dimensions of learning. So what we find in general is that agents that are trained in multi-agent settings, particularly many agents in the same environment, actually it takes them longer to learn basic skills.
Maybe you should give them chemical trails.
We've in fact talked about giving them in fact, I think we've even tried like breadcrumb trails. Yeah. There's there's a notion of stigmergic memory. That's a special case where the agents actually modify the environment as a way to sort of offboard their memory and potentially make it readable to other agents. That's something that's enabled by MettaGrid as is, because agents can pick up resources and then put them down, and then the other agents can see them, right? So even as it stands, agents could learn to use that to communicate or to outsource their memory. In general, we don't see them doing it yet, but I think it is just a matter of time. So yeah, there's lots of possibilities in this. It's like actually quite a fun lab to study this kind of stuff. Was there one other question?
Yeah, I just wanted to note that I think actually it's more of a gradation also, like what you call a qualitatively new skill that a group can have. So if an individual can remember like sequences up to 3 things,
Right.
and the group up to 10 things, then it's not a qualitatively new skill that they've unlocked.
Correct.
Quantitative improvement.
100%. Yeah, and this is like Mike Levin's argument that all intelligence is collective intelligence. Like even individual cells have a minimal kind of memory and a minimal kind of, I would say valence. This was a question that Riff asked yesterday, right? But it's very minimal. But when you stack a bunch of them together, then you get this kind of compounding effect of, okay, now you can remember really long sequences, or you can have really subtle valence states, or you can have, really sophisticated planning or whatever on the building blocks that are very simple at those things. But my belief is if agents don't exhibit any memory individually, then it's much less likely that they'll exhibit collective memory. Right. If they do, fascinating finding, right? That suggests that the memory isn't actually like in any of the agents. It's like in their interactions or something. Cool, amazing. That's a great result. Love to see that paper. But yeah, so far we haven't seen any sort of like step change in capabilities when they enter groups. Yeah.
And do you view any of these like giant game of life results as being evidence of that kind of step change? Like an individual cell
That's a good
game
question.
of life
Yeah.
doesn't have any capability except responding to the rules.
Yeah.
But clearly game of life.
Yeah, I would say yes. I would say that is. Yeah, I think that's a case.
Do I win the prize?
Do it in MettaGrid, then yes.
I certainly build game of life in that.
Yeah, do it. Let's see. Okay, so anyway, this is just a cool video that demonstrates an agent learning in context a novel sequence of steps that allows it to obtain reward. So it goes through trial and error, trading resources in different parts of the map, and then discovers that this red bucket on the bottom is like a sink. When it drops things in that, it gets nothing out. And then it learns through this trial and error not to drop things into the sink, and instead to navigate the other items in the list or in the sequence in order to obtain the reward that it's looking for. And this was accomplished through many, like tens and tens of thousands of training environments where agents had to navigate arbitrary sequences of tasks in order to obtain reward, each time a different sequence of tasks. And through tens of thousands of exposures, the agents learned, oh, okay, there's actually this more general principle of how do I figure out what the sequence is. And I think this is a really cool result, because all of the environments, all the training environments were algorithmically generated. There was no human building these environments. There was no human even like using a tool to help them make environments. Literally, they were just like, these are the parameters that we think will lead to good training environments. And then boom, here's 50,000 training environments. And it turns out that that's good enough to help agents generalize these in-context sequences of learning how to navigate, admittedly, small environments. So really useful for single agent metrics. Another single agent metric that we are going to be, if we haven't included it in the public repo, we will be later this year, is an ability for an agent, or for us to predict what actions an agent is going to take next. So this is like peering into the agent's brain. In our default agents, we have these RNNs with an LSTM, and we basically have trained an AI model to look at the LSTM state and predict what actions the agent will take on the next 10 time steps. And it turns out that after sufficient training data, the AI can actually predict with like 80-90% accuracy, 70-80% accuracy what the agent will do on the next time step, and with like 50% accuracy what the agent will do like 3 or 4 time steps into the future, which is much higher than random chance would predict. So again, single agent metric that's really cool. Does the agent's memory tell you something about what its plans are? The answer is yes. We've demonstrated that now. We're going to include that in the repo soon if it's not already there. Please add your own. There's many more single agent metrics. The next one here is multi-agent metrics. So I spent a lot of time this week at my other talks talking about multi-agent metrics. What I didn't say, or at least didn't say very loudly, is that all of those metrics are really great in theory and also really computationally expensive. And so we're actively looking for people who are interested in taking those good theoretical metrics and making them computationally tractable. Abel and I talked a little bit about this yesterday. So if you've got a way to measure multi-agent cooperation, emergence, or well-being, we'd love for you to add it to MettaGrid. These could be, for example, a more computationally tractable version of causal emergence 2.0. Hopefully, there'll be something like that soon. You might have some metric for how agents learn from each other. Hey, I've got a multi-agent setting, and the agents do this if there's no other agents around, and they do that if there are other agents around. And that affects their future behavior in these ways. Great. You've got a multi-agent metric there. Throw it into MettaGrid. Let's see how it measures up. Or maybe you want to have some sort of thing that's trying to predict the past history of an agent based on its present behavior. Like really good psychologists seem to be able to look at someone, talk to them, and figure out what kind of childhood they had, right? Wouldn't it be cool if you had some way to look at a group of agents and how they interact with each other and to sort of like diagnose them as being narcissistic or otherwise just based on their behavior and then predict, oh, this agent must have had a really tough training environment or set of training environments. This other agent must have had very loving parents, whatever. That'd be really cool. So we're like making this open call to everyone here and soon everyone in the world. Like if you've got ideas on how to do this kind of stuff, please put them in MettaGrid. Then as soon as you do, it gets applied to all of the architectures and all of the training regimes and all of the environments. The cool thing about these metrics is they'll just run on everything. We'll just add them to our profiler list. So anyone in the world who submits a novel architecture or a novel multi-agent environment will be scored on, causal emergence, on, how well are the agents learning from each other, on what's their upbringing like, et cetera. Like all of these will be scored. And it'll be a really cool scorecard for researchers from everywhere to actually see, hey, what are my agents like in groups? Does this all make sense? Yeah.
Just to clarify slightly, you're saying that Metta's commitment is if we give you something that is reasonably computationally efficient, you will use your cloud resources to run it and score it and put it up for us.
Correct. Yeah. I mean, reasonably, we need to be specific and whatever, but at a minimum, it'll be included in the open source package. So people who are running it on their own clusters and their own laptops will get it for free. But yeah, if it's something that we're increasingly going to be hosting stuff in our own cloud cluster. And so, yeah, if it's useful and relatively efficient, then we'll just include it in there. And we'll include a link to the paper about it if you've got one and, whatever. And yes, this will be an opportunity for you to get acclaim for your great metrics, right? Please, yes, that would be great. Okay. The fifth mode, this is one that I'm super interested in as a researcher, is the relationship between metrics of cooperation and emergence and the success of groups at achieving reward. And I think this is going to answer your question, Sarah. So reward is reward, right? Like there is something that we're rewarding agents for doing. In MettaGrid, we're generally rewarding them for obtaining hearts. Right. It's for those of you who didn't notice, MettaGrid has two T's. That's metta is the word for loving kindness. I think in Sanskrit, someone can keep me on. Yeah. So the way that we reward agents is for obtaining hearts. And we'd like to know what's the relationship between obtaining hearts and these metrics of cooperation and emergence. Is it a tight correlation, or actually are these kind of semi-orthogonal dimensions? So for example, let's say that you pick a particular environment and a particular set of agents. Is there a particular metric like causal emergence, where the more causal emergence you see in a group of agents, the more likely it is to get a lot of reward as a group? That would be a very interesting result. Or maybe it's not just causal emergence. Like maybe that's not enough, because by the way, you can get causal emergence without getting reward, just by being very synchronized with each other. So maybe it's some combination of causal emergence and diversity of behavior, right? If the agents are forming a larger whole and they're all acting differently from each other, maybe that's predictive of the team scoring a high reward. And again, all of the ideas that we've all heard about or thought about in terms of group psychology or cell biology, you can just toss them in here. Maybe it's something about the diversity of experiences that they've had, right? Like maybe that predicts how well their teams are going to score at reward. Or maybe it's something about the amount of surprise in their movements, right? Like agents that are constantly synchronized with each other, maybe they score better, or maybe they score worse, whatever. So I would love for us to see as a field a really clear map. Hey, these are the factors that lead to or predict teams scoring really well together. And then that research can get ported back and see if it applies in other fields like organizational psychology or family dynamics or political science or cell biology or whatever. The idea is that this can be a simulation environment to test those ideas quantitatively and then export them to other fields. Yeah.
Yeah, I was actually thinking of the rise of the machines kind of thing. Would you make like an environment where there are like stupid humans and then super smart AI, and then see if the super smart AI cooperate to like do bad things to the humans? Or something?
Yeah, sure. If you've got metrics for it, you can test that. Yeah, yeah, absolutely. Okay, the last one here is one that's a little bit of a twist, but I think is important to name, which is actually to create an ecosystem with a prize pool. So many of you guys are probably familiar with the ARC benchmark, the ARC AGI benchmark, which has been really effective at recruiting a lot of independent researchers, really smart people, as well as AI labs and academic labs, in part because they actually gave them money if they were good at it. Right? So literally, they're like, if you solve these tasks, right, at above a certain score, then you will get a prize. And it's like $1 million, quite substantial. Funny enough, Softmax early on was actually testing its ideas in ARC. We ended up not working more on that because it was hard to do cooperative stuff in ARC. ARC is very like, solve this problem, solve that problem. But we would like to create a prize pool. So if any of you guys work with foundations that are interested in this kind of thing, come talk to me, where there's actually an economic incentive to reward the development of cooperative AI and emergent AI and compassionate AI. And so the idea would be you could either reward agents that are especially cooperative. So whoever develops those agents gets cash because they built the most cooperative or emergent AIs. Or the most interesting metrics, right? So like maybe there's a really cool metric that allows you to predict cooperation or allows you to detect emergence. Great, that could also be something that's rewarded financially. Or someone brought up earlier, like novel environments. Maybe you've got some really creative environment where when the agents, grow up in that environment, then they're more cooperative later on. In my dream, basically there's like money for all of these things that's cycling through so that the field isn't just financially motivated by capabilities, but is actually motivated by cooperation and alignment. Yeah.
I'm realizing I'm suddenly a little bit confused with this last one of what you mean by modes. I'm thinking of modes as kind of software libraries on top of some base layer, but this obviously isn't.
Yeah, no, I could call it something else. Modes of interacting with MettaGrid, you could say.
But the other ones are kind of reified in software. They're libraries that are on top of the base library.
Correct.
You don't have to use them, but you could.
Yeah, that's right. So like modes of using Salesforce, right? You can like use Salesforce to manage your CRM. You can use Salesforce to send marketing emails. You can also buy Salesforce stock or whatever. It's like a different mode of interacting with Salesforce. This one is like a bit of an outlier mode, but yes, you're correct to pick up on that. But I don't know who's in the audience, right? Like some people here at least are interested in funding this stuff. So yeah.
So if you zoom out from humans a bit and look at the way we interact, one of the ways we interact is through trade and making things for each other, giving things to each other, making dinner, making a software platform. It seems to me like if you zoomed out, you'd see a lot of organisms, at that scale. And
at which scale? Sorry.
So my question is, what's the larger organism that MettaGrid is a part of in the sense that what's the first product? What's the first dinner or software platform that is going to be made out of it, in your opinion? Yeah, well, I think the first dinner or platform that's going to be made out of it is going to be a hosted, like benchmark or competition, right? It's like instead of just using it locally or in your laptop, there'll be some sort of authoritative place that you go where you see how other people are doing in particular environments according to particular metrics. That sounds like science to me, and I'm thinking more like... Oh, like something people pay for? Yeah, like a thing where someone's like, I need something, and they go and they pay money. Yeah, I mean, the truth is that
our company is at a similar stage to where OpenAI was before they developed GPT, where they're like experimenting with a bunch of stuff, showing some cool capabilities, and like, I don't know, how are we going to make money? We'll figure it out. It's like kind of our perspective. One possibility is that we end up creating like cloud infrastructure for multi-agent researchers, and we charge them to use it, right? Or something like that, right? Or another possibility is that through the cooperative behavior of agents in MettaGrid, we're able to facilitate people solving multi-agent coordination problems like, I don't know, some sort of trade-related thing, like how do you best organize trade flows in a particular state or something, like, I don't know. But that's not our focus right now. We are just focused on getting the principles right and showing that multi-agent cooperation and emergence can happen.
I would argue that the principle of language
Yeah.
is actually maybe the linchpin principle that has already been gotten right.
Mm-hmm.
Because it allows my mind and your mind to have a shared workspace.
Yes.
And a shared way of serializing our internals.
Yeah.
Which is imperfect.
Yep.
KV cache is lost when you serialize into text tokens.
Yeah.
But, so I'm kind of like, what if that moment that you're looking for happened in 2018,
Mm-hmm.
and that's actually, language is really the key to working together and becoming a whole together.
I hope you're wrong, but you might be right. Here's why I hope you're wrong. Because humans are capable of cooperating before they speak language. Right, like baby, I have a 7-month-old, right? Like the 7-month-old was not able to speak in sentences, still is not. And nonetheless was able to, like my wife and him were able to coordinate, feeding, sleeping, etc. And I was able to an extent, right? And so like, you could say that's a kind of language, right? Okay, but at that point we're like really futzing with the definition.
What if the attention layer,
Mm-hmm.
right? What if the attention module in the transformer is
Yeah.
what allows the recursive calling of established shared symbolism, whether that's
Absolutely,
or
yes.
with the hand or
Yeah, so it's worth saying that there is there are multiple ways where agents in MettaGrid are able to exhibit emergent communication already. One I already mentioned, which is stigmergic memory. So we're all standing around something, and an agent drops a resource, and all the other agents see that. And the agent picks up the resource, and all the other agents see that, right? Another one would be like bee dancing, right? Like the other agents can see you moving. And so, well, at least if they're nearby, just like bees can see you if you're nearby. And so like you could learn that moving back and forth communicates certain information, or that moving in circles communicate, like that's already possible. And I'd love to see a researcher show the first bee dance in MettaGrid. That's already possible. The last possibility is we've actually built an explicit mechanism, which is agents changing their color, which is like a semaphore, basically. So agents can choose to change their color, and all the other agents around them can see the color. And that's also a way that they can communicate. Now, the reason that I say I hope you're wrong is because I would like to see language emerge, not be built in, because that's what happened in living systems. Like language it evolved, it emerged through interactions. It wasn't something that was pre-programmed. English was not pre-programmed, right? Like the basis vectors were not preset to be English or Chinese or any particular language. It's just, it happened. So that's what I'd like to see.
It feels scientifically fun, but it's less being part of a whole. Because we already have a language, and if machines cook up their own language, well, it was really cool. But anyway, they're not part of this.
Yeah, well, I don't view those as mutually exclusive, right? So like when we encounter, I mean, we haven't in a while, but when we encounter like a culture that hasn't been touched for hundreds or thousands of years, right? They have their own language, and then there's this process, sometimes slow, right? Yeah, where like so yeah, we can shortcut it by saying, okay, English is the lingua franca, no pun intended, right? It's like, that's what it's going to be. But I'd rather see the agents organically learn their own language and then encounter humans that have a different language. And then we learn to speak each other's language. To me, that's like a more authentic kind of organic alignment than predetermining the language of the MettaGrid agents. But as I say, you could be right. It might be that the right thing to do is just to train them on English. And the cool thing is people can do that. They can submit LLMs trained in English into MettaGrid, and we can see if they're better able to communicate in MettaGrid. Like maybe they end up using their color as a way of communicating words. Like they could do that. They could actually change their color, time step by time step to communicate one character at a time, or 5 characters at a time or whatever. And then maybe they're going to end up speaking English to each other already. That's something they could do. So it'd be really interesting to see if that's what happens.
I guess I would expect their world is really quite a lot simpler than ours. So.
But in general, yeah. I mean, yes, you could build a billion by billion,
but even
thing.
then,
No, of course, you're right. Even then, it's going to be simpler than ours, yeah.
So I would expect them to not need all of our human natural language.
I would expect so too, yeah.
It's surprising, like...
Yeah. I mean, I would expect so too. And so, maybe the right move, I mean, for someone here is to train an LLM on like only 1,000 words of English or only 10 words of English, right? Including like the movements, like up, down, left, right, whatever. Like maybe that's the thing to train it on and see what happens. I don't know. Okay, so this is the weird mode to interact with. If you've got money and you want to support this, then you can help us put together a prize pool. And the idea, in my mind, is to create a Schelling point. Who here is familiar with the idea of a Schelling point? Yeah, okay. I'll just briefly run through it because I love it so much. Schelling point, this great concept by the guy Schelling, I think his name was John? Thomas, thank you. Got the O, but not the name. Okay, so the way that it was explained to me is back in the 1900s at some point, 1940s, 1950s, the question was posed, you and a friend are on the phone with each other and you agree to meet in New York City, in Manhattan tomorrow. And then the phone connection dies and you need to figure out where and when to show up in Manhattan. Guessing where your friend will also know to show up where and when in Manhattan. And the question was asked to people like, when would you show up? Like if you didn't know and they didn't know, like when would you just guess that they're going to show up? And the answer was noon. Yeah, like everyone sort of knew that everyone knew that noon was the time. And then the question was like, where would you show up? And anyone want to guess the answer? Don't say it if you knew the answer. But anyone want to guess? Like where would you show up in Manhattan if you didn't know where the other person was going to be?
Middle of Central Park.
Empire State Building?
Those are hard to see someone in.
Times Square?
Paris is better.
Yeah. The answer was underneath the clock in Grand Central Station.
Right.
Yeah. Anyway, back in the 50s, that was like the obvious choice, right? So whatever. So the thing about this is it's about common knowledge, right? We're trying to create common knowledge that there's a field of multi-agent cooperation, emergence, and compassion. And in order to do that, we think it's valuable for there to be other people know that the place that you go to do this kind of research is this open source framework called MettaGrid, where there's other researchers doing metrics, other researchers doing architectures, other researchers doing environments, and there's money to be had and compute to be had if you're successful at moving the field forward. That's the ecosystem that we're trying to create. So that's the last mode for interacting with MettaGrid that I'm going to talk about today. So to summarize, we think that the approach of values alignment is not working. As AIs get more sophisticated, it becomes harder and harder to successfully control them. We need to find a different approach. The approach of organic alignment seems to work in living systems, and we think it can work in sophisticated AI systems. There is new math for emergence and well-being that's just getting started. It's not computationally tractable yet, but there's good principled foundations that we can build on. And there's tools for running open-ended multi-agent simulations with arbitrary architectures, metrics, and environments. All of these things that I've talked about here, 100% of these are free and in the public domain. There's nothing that I've talked about today that is proprietary, with one exception that's going to be public domain very soon. So we're really being very upfront with all the research here. There's nothing secret in terms of MettaGrid, in terms of the environments, in terms of the metrics. This is for everyone to contribute to and everyone to participate in. So there's really no reason, if you're in this field, not to give it a try. And the way that I now think about it is we're not necessarily trying to get rid of control-based approaches to alignment. We're just trying to recognize that those belong when agents are really simple and really controllable. So you can graduate from this control-based approach to an organic alignment approach where we and the AIs are part of a larger whole together. And if you find this compelling, I hope you will actually put some mental cycles into this because it may change the trajectory of society in a much better way. That's it for today. Any other questions before we wrap up? Riff. Yes, please.
One is kind of a conceptual question. So when you conceive of soft, like in terms of how you think about soft mechanism, how do you view the division between building stuff you expect researchers outside the company to use versus using the tools yourself to do research to push forward on these?
Yeah. We view it in a similar way to like how Amazon ended up developing AWS, which was like at first it was 100% internal. They're just like, how do we build good server infrastructure for Amazon? So for us, similarly, how do we build good infrastructure for training and testing multi-agent systems? But increasingly, as the code's gotten more stable and as we've had more people interested in using it, the focus has turned more to, in balance to like, okay, and how do we also make this useful for outside researchers? So these days it's like, somewhere like 50-50, probably still a little more internally focused.
Cool.
Yeah.
I just have one more.
Yeah, please.
So briefly, great talk. Thank you so much
Thanks.
for all this.
Yeah.
There was a different talk I was expecting to see today, but I wanted to see.
Okay, what's that?
Which was basically like, what are your great results? Like, what experiments have you run?
Yeah.
What have you learned? What have you almost learned? What
Yeah.
you can't learn?
Sure.
What's working? What's not working?
Yeah.
Is there any way we can see that talk?
Yeah, that talk will probably be the talk we give at the A-Life conference in October, for those who are going to be there. Or one of the talks we're going to give there. Yeah, so I showed like a few results, particularly in the single agent case where agents are able to navigate sequences and remember and so on. We viewed that as a building block to sophisticated, or a prerequisite for sophisticated multi-agent interactions, and we just got that result last week. So now I think we're going to start to see more interesting multi-agent results, but we just haven't had very many so far. This is like very much in its infancy. So yeah. Other questions?
Well, that was going to be a question.
Yeah.
But the other question I have is, like outside of this, right, there's lots of startups and the labs, whatever, just trying to build out agents capital to do various things, right?
Yeah.
And sort of tack on various capabilities. And
Yeah.
the one that struck me, sort of in relation to the language question, sort of not exactly related, is like a better version of memory, right? Which seems like a huge obstacle right now with the way that you interact with AI. And
Yeah.
context is degrades and
Yep.
they're very bad at long-term thinking. Whether or not like adding a database on fix that, I'm somewhat skeptical, but I wonder if you thought about trying to, hey, you give them 10 colors, like
Right.
you give them some number of bits of permanent memory.
Yeah. So they have LSTM state. I believe it's 124 bytes of memory that our default agents have. But you can bring your own agent to the party with any kind of memory you want.
Even inside the network, right? Like that also degrades over time, right? So like,
How so?
maybe I'm misremembering how the LLC is structured, but
I mean, it's just a memory vector, right? So the agent can use it however it wants. It can overwrite it, it can preserve it, it can use certain sections more than others, like that's up to it. And again, we're open. If people want to have super big memories and super small compute units, and they think that that's going to do better, great, let's try it. Also, people can try memoryless agents, where there's actually no stored memory inside the agent. And if they want to remember things, they have to leave markers in the environment. Like that's another approach. It's just purely stigmergic memory. Or interaction-based memory, like the way that the agents interact with each other. Like we're so open. Like we do not have a perspective on which of those is right. Yeah.
My mind is going towards something like what if I use this as a substrate for doing like social science research or something, which is to say suppose I'm interested in something like intergenerational knowledge transfer.
Sure. Yeah.
Like setting a lifespan to a given agent and then introduce different generations of agents.
Yep.
And then I'm interested in I'm interested in something like how older generations of agents pass on patterns or behavior patterns down to
Definitely.
younger generations.
Yes.
I could do things like that presumably.
Definitely, yeah. There's a technique in reinforcement learning known as kickstarting, which is basically that. So you have an agent that's already been trained, it's learned a bunch of stuff, and then you have a novice agent, perhaps just initialized, and you basically give it access to the internals of the parent or of the teacher. Teacher is the term that's used. And you can see how much that helps the student to pick up skills more quickly. That's traditionally the way that kickstarting is used. But you could also use it to see, do they pick up certain habits that are unhelpful or something like that. Yes, you can definitely use it for that.
Yeah, interesting.
Cool. Okay, well, that's the end of today's talk. I'll be around the rest of today and tomorrow. Let's chat. Thanks.
Thank you, Adam.
Yeah, thanks. Thanks for the great questions, Rick. I told Alan you asked the best questions.
Certainly. And you just ought to ask them those questions.
Yeah, also the best.